hear me. So thank you very much, India, and pleasure to be here. So I think I'm not actually representing the industry here. I will be trying to undermine what we've been doing the last probably almost decade. And that's why the title of the talk, Quo Vadimus, means where are we going? So probably some of you have seen these parts of this lecture many times, so I like to start with a quote from Weil, who was talking very poetically about symmetry, as wide or as narrow as you may define its meaning. It's one idea by which we try to comprehend and create order, beauty, and perfection. The term itself goes back to ancient Greeks, so Plato, for example, believed that all the stuff around us is made of symmetric polyhedra that we nowadays call Platonic solids. And the Greeks really attributed a very prominent place to geometry. According to the legend, Plato had this inscription on the entrance to his academy that is reproduced also in our Department of Mathematics in Oxford. Translated from Greek, it says that nobody who is not proficient in geometry is allowed to enter. So the geometry that the Greeks conceived, or at least formalized, was the only one that existed for more than 2,000 years until the 19th century, where alternative constructions were introduced, was given the name of non-Euclidean geometry. And it created this kind of zoo of different geometries that were disconnected and studied separately, and it required the insight of Felix Klein, I mentioned in the introductory remarks yesterday, and that's also the reason for this entire hub named after the Erlangen program that introduced group theory as an organizing principle and design principle in geometry. So the idea that you can define geometry as space equipped with some group of transformations, and you study properties that remain invariant under the action of these groups. And for example, the classical Euclidean geometry, right, from 2,000 years ago, arises from the group of rigid motions, the Euclidean group. So it was a very influential idea, not only in geometry, of course. So geometry took another 50 years to integrate it with Riemannian geometry, mainly the works of Cartan, but also adjacent fields like physics. So here probably the most remarkable result is due to Erwin Noether, who proved that conservation laws in physics in certain physical systems can be derived from first principles of symmetry. So conservation of energy, for example, comes from the symmetry of time, and these ideas evolved in the 20th century to the foundations of modern physics. So everything that we know or understand in physics can be derived from consideration of symmetry, right? So the external symmetries of space-time, the Minkowski geometry that arises from the Poincare group, and the symmetries of the quantum fields that give rise to different fundamental forces and interactions. Here I think it was beautifully captured by Philip Anderson in his famous essay, More is Different. He said that physics is the study of symmetry. So a similar thing exists in the field of machine learning. If you look at deep learning architectures, different neural networks that were designed for different types of data, for different problems with different historic context, they all seem completely disparate, completely disconnected architectures, and that's why there is a little bit of this flavor of witchcraft and hacking that exists in the field of deep learning. But we actually try to unify it through the same perspective that Klein proposed 150 years ago, which is a group theoretical framework that we call geometric deep learning, and basically deriving all architectures or almost all architectures that exist and being used in practice from the same fundamental principles. So if you look at a very simple setting of machine learning, right, supervised learning, like image classification, basically you try to solve a high-dimensional function approximation problem, right? So let's say I want to distinguish between cat and dog images, so I can represent cats and dogs as vectors, feed them into some black box, right? That is a parametric family of functions, let's say a perceptron, a very simple neural network, right, with fully connected layers. And we try to find the weights that will approximate a function from a finite sampling. So we know that these architectures, right, in a very simple setting, if we just have one hidden layer, are universal approximations. So I can approximate any continuous function, or even more general class of function if you want to be completely rigorous, to any desired accuracy, right? So it's usually a non-constructive result. It doesn't tell how, it doesn't tell how many neurons, how to find the weights, but it is important to realize that such neural networks exist. The problem comes when you try to see how to apply these results in practice, and the practical consideration is that when you deal with multi-dimensional inputs, right, when your function operates not on two-dimensional inputs, not on three-dimensional inputs, but maybe 1,000 or 1,000,000 dimensional input, we run very quickly into the problem that is known because of dimensionality. So it's a collection of statistical or geometric results that basically tell you that the number of samples that you need to take will scale exponentially with the dimension, right? And for any practical purpose, even dimension 10 will probably give unreasonably large number of cats and dogs, so probably more than the number of not only cats and dogs, but all organisms that live on Earth. So the idea of geometric deep learning is to resort to different types of priors, so not the usual priors that classes of functions that people assume in functional analysis, but a different type that we call geometric priors. And the underlying assumption here that our signals are not just d-dimensional vectors, they are functions that live on low-dimensional spaces. So, for example, something like a grid. And on these spaces, we have well-defined geometric operations that we can formalize using the group. And for example, on a grid, I can translate points, and the representation of this group acts as a shift operator on the image that is defined on the grid. And then I want to define a class of functions that take as input these signals, and they interact in appropriate way with the group that I'm assuming, right? So for example, I can assume translation invariance, right? Which is a very reasonable assumption in signal processing or in image analysis. No matter where the cat is located in the image, I still want to classify it as a cat, right? So it's convenient to build in such a prior into my architecture. And if you think of the classification problem as represented like this in an abstract way, right? So we have two different objects, and I want to be insensitive to the orientation of these objects, so it's very difficult to learn these kind of transformations. It is possible, as practice shows, especially recently when these groups are low-dimensional, right, or they are finite and have small number of elements, but in general, it takes an effort, and what is probably more important, it takes significant amount of data. So I need to show the neural network examples of different transformations of the same object. So if I know a priori how these transformations look like, I may do it by data augmentation. So instead, in these geometric architectures, I can guarantee by design, by building an architecture appropriately, that every orbit of the group will be mapped to the same one. Right? So I significantly reduce the sample complexity, of course, at the expense of having some maybe more elaborate architecture. And actually, this is completely not new idea. So the very famous or infamous book, depending how you interpret it, the perceptrons from '69 by Minsky and Paper that is blamed for introducing the first AI winter that killed the neural networks. The early works on neural networks actually had already these results, so they called it the group invariance theorem, but they didn't really evolve it too much. So I think John Shaw Taylor in the 80s and the 90s was one of the first to actually analyze neural network architectures, but I think it's fair to say that it was probably in the last decade that these architectures have become really useful and led to practical results. So if we look at the computer vision community, so the idea of invariance of some description of an image or portions of the image that are insensitive to geometric transformations has been a classical staple in the last 20 years or so. So one of the most cited papers in computer vision, the SIFT, scale invariant feature transform, try to do exactly this. So extract some regions in the image that are stable under not only rotations and translations, but also more general affine or perspective transformations, canonize these little patches of pixels and then represent them as vectors and then feed to a simple classifier like an STL. And this idea that you can take an image and then basically do this kind of invariant representation is very appealing, but you lose in this way a lot of information because you lose the geometrical relations between the objects, right? So this was an example where the entire image undergoes a rotation, but I can potentially, well, if you want, of course, rotate different parts of the image, right? And it still will be represented by an invariant representation in the same way, but of course we cannot say that this is the same person. We cannot even say that this is a human face, right? Unless you are Picasso. It's actually known as the Picasso phenomenon, right? So that you can take a face and do some weird things to break the traditional geometric relations. So we need a more general principle, and this is the principle of equivariance. So invariance is a special case of it. In this case, the input and the output space have similar structure, and then the action of the group on the input should should be transformed into the same action of the group on the output, maybe with different representation, right? Because the dimensionality, for example, of the input and the output spaces might be different. So in the example of image or computer vision problems, let's say that you want to segment the cat from the background. If I move the input image, I want the output to be moved in the same way, right? So what we gain from the equivariance constraint is what we can call symmetry consistent generalization. So again, if I have two objects that undergo the same transformation, let's say rotated by the same angle, so we want to avoid this situation. So we want to guarantee that the representation in some intermediate feature space of these two rotated objects will be consistent. So basically, by design, we guarantee this situation and not the previous one. So historically, the first architectures that implemented these geometric principles, maybe without really understanding or acknowledging it, were inspired by the works in neuroscience, the famous work of Hubel and Wiesel from Harvard that won the Nobel Prize in the 80s, the study of the visual cortex of the brain. And basically what they discovered is that the neurons in the visual cortex are locally connected, and they also share parameters that they refer to as receptive fields. And this was first replicated on a computer by Unihiro Fukushima in the architecture that was called the neocognitron, and then famously by Yan LeCun in convolutional architectures that initially actually were not called convolutional, and only in subsequent papers were given these names. So these are the CNNs, and the main two principles that underlie them is the idea that you have locality and shared parameters, right? So not every neuron connected to, in the output connected to every neuron in the input, and the parameters are shared across locations. So if you look at the structure of the layer, if you represent it as a matrix, you have an order of n, or if the receptive field is small, order of 1 parameters as opposed to order of n squared. So it reduces significantly the number of degrees of freedom, and this allows to tame the recursive dimensionality. There are some other considerations like multi-scale representation that I will not go into detail. So there is actually a beautiful paper by Stéphane Mallat and Joan Bruna studying why actually convolutional neural networks work. But from our perspective, this is part of the general framework. So the idea that you can start with some domain on which our data lives, and subject these points on this domain to some transformations, some group, which acts for some group representation on the input data, and then you can apply some function to these signals that respects this group, right? So you can actually derive convolution as the only linear operator that is equivariant with respect to translation, right? So that's how it's appropriate to define convolution, and not just to give a formula and say that this is what it does. You can generalize this principle to other types of data. And so if you have, for example, a chemical compound that you want to predict its properties, you can represent it as a graph. So this is actually a compound that probably all of you were consuming in the break before. So this is a molecule of caffeine. And basically the underlying symmetry here is the permutation of the nodes. So we don't have a canonical way of ordering the nodes of the graph, so we need to be able to deal with any permutation. And in chemistry, it's important, right? Basically, it tells us that no matter how we order the nodes of the graph or the atoms of the molecule in a computer, it still has the same chemical and physical properties, right? So the kind of architectures that implement this principle are graph neural networks. So they work by principle that is called message passing. So every node receives information from the adjacent nodes connected by edges. And basically this, again, implements the principle of locality and shared parameters, because this aggregation operator is the same and replicated everywhere on the graph. And then, of course, you can apply several layers like this. So this operation is permutation equivariant. And then if you want to pull everything together to predict the property of the molecule, you can combine it with the permutation invariant readout. So again, the same principle implemented with a different symmetry group and on a different type of data, right? So the same instance of the geometric deep learning blueprint. And we can apply these principles to all sorts of data, so more or less anything that exists in this field can be thought from this perspective. Well, it's convolutional neural networks, right? So you choose a domain, and in this case, a translation group, you get CNN. You choose a graph with a permutation group, you get a GNN, and you can also do more exotic things like, for example, do convolution-like operations on manifolds, So if it sounds exotic, it's actually very practical. So some of the early applications that we worked on were in the field of computer vision. There was a company that one of my students was involved that was acquired by Snap 4 years ago. So they are doing 3D avatars from video input, so it involved these kind of geometric architectures. And also I've been spending quite several years now working on in the field of structural biology, so using geometric convolutional architectures for predicting properties and designing new protein molecules. So it gave quite incredibly a lot of mileage to my collaborators to publish several papers in Nature. You can also print these proteins, right? And this is what politicians like very much, right? So you can say that this is what we are doing, right? This is what we are working on. So you can actually show it and present it as gifts. So this is an important protein in the protein degradation mechanism that was printed. Anyway, so basically, more or less anything that exists in the deep learning zoo can be thought about from this perspective. So in a sense, it's a kind of universal blueprint, right? So everything fits into this blueprint. What is also interesting is that you can create new architectures in this way, and probably the prominent example are geometric message passing or geometric transformers. And same way as in physics, we have this distinction between external and internal symmetries. In case of graphs, for example, right, or more generally in geometric deep learning, we can also distinguish between the symmetries of the domain and symmetries of the data. And molecular graphs are a good example, right, because they have the identity of the nodes, right, so the type of the atom, but these are also geometric graphs. So they live in three-dimensional space, so you can subject the positional coordinates of the nodes to continuous transformations, like rotations and translations. And in this case, again, we want to say something like, no matter how I place my molecule in the space, I want the properties to remain the same, right? And basically here we have, again, this combination of two symmetries, permutation of the nodes of the graph, and transformation of the data that lives on these nodes, right? In this case, these are the atomic coordinates. You can create special message passing architectures that respect both symmetries, and this idea was very powerful and was implemented by DeepMind in AlphaFold 2, so the famous program that predicted the structure of proteins from amino acid sequences, and this is what brought the inventors, Demis Kassalis and John Jumper, the last year Nobel Prize in Chemistry. So and at this point, you could argue that this is probably a very glorious application of these ideas, right? So the Nobel Prize was given at least partially in recognition of geometric deep learning ideas, so they lived happily ever after. The problem is that actually the same DeepMind abandoned these ideas altogether. So AlphaFold 3 completely dropped all equivariance. So it is all atom plane transformer with data augmentation trained by brute force, because these architectures are much simpler and you don't need to work hard to implement them in a special way. And actually the first shots, so this is from State of AI report that is produced every year by Air Street Capital, so a famous VC firm. So it quotes the first shots were fired by Apple. So this is actually one of my students, Ahmed El-Hajj. So when you start a PhD, the best idea to say that everything that your supervisor has been doing in the past 10 years is nonsense. And this is exactly what he did. So basically they showed, so that was also a problem from chemistry, generation of molecular conformations without any equivariance. And it actually works well. And you can also show that, so this is a follow-up paper where he shows that he can introduce in a soft way the equivariance rather than baking it into the architecture. And actually in some cases, it works better than full equivariance. So there is some kind of, so it's not just a hard choice whether you're completely generic or you're equivariant. It can be halfway through, right? So it can be approximately equivariant. And in many cases, it works better. And so the purpose of this talk, right, or the remaining time, I would like to try to answer the question called Vadimus, right, or where are we going? So are we going towards this shiny and rainbow castle of equivariant architectures where everything is beautiful and there is beautiful group theory and mathematics, or we go back to the brute force data augmentation, compute-only approaches like transformers. So I think that what we see here and why the field moves towards the brute force approach is the instance of what is called hardware lottery. So this is a term that was introduced by Sarah Hooker from Google. And she was saying that basically it's the case where research ideas win not because they're suited to the existing software and hardware architectures, not because the idea itself is superior to alternative research directions and ideas. So convolutional neural networks is actually a good example, right? So translation is not the right set of transformations in computer vision. So we usually deal at least with perspective transformations. And yet this was the winning idea because it is easily implementable on digital signal processors, the DSPs that existed in the 80s and the 90s when Lekan was working at Bell Labs, and then on GPUs. So this maps nicely to these single instruction, multiple data or CMD architectures that exist in hardware, right? So it is actually that the hardware lottery discourages trying out other things because you cannot implement them efficiently on the hardware, on the GPU. And it happens that transformers are efficiently implementable on GPUs not because they're somehow suitable or somehow appropriate mathematically, right? So transformer is actually a graph neural network, right? So it inherits from graph neural networks the permutation equivariant property. Now you can ask, transformers are the most prominent in natural language processing applications, right? So language is probably the last thing you can think about where you have permutation invariance, right? So the order of words in a sentence doesn't matter. So the only thing that really breaks this symmetry is positional encoding. So transformers would not work without positional encoding. So why they are still used for this task where they apparently not appropriate is because of the hardware lottery. So basically, if we want to revisit the idea of geometric deep learning, right? And it seems like the end of it, right? So we are moving away from mathematically motivated algorithms to just brute force because it's easy to implement on the GPU. We need to remember that this is what the picture that we've seen before, right? So we have a function, we had its input that is acted on by the group, and we wanted the function to respect the action of this group, right? Either in the form of invariance or equivariance. So something like this, right? So this is an invariant function. Now we need to remember that it's only half of the story, right? Because neural networks have also extra input, right? So these are the parameters, the weights of the neural network. So what we really are interested in functions that are acted where the x and the theta spaces are acted upon by different groups, right? So we have another group, let's call it H, that acts on the parameter of the neural network. And I'm arguing that this is very interesting kind of symmetries that we need to look at. And we can learn a lot from it, how neural networks work. We can also bake some invariance into these architectures and do cool things that are probably not possible otherwise. So just to motivate why this makes sense, so if you consider very simple neural network architecture, so these are just perceptron with one hidden layer, and let's ignore here the biases. So that's how it is connected, right? So I have weights from x to h, right? So h is the hidden dimension, and then we have outputs flat, right? So I can write it in this form. So I have the input vector x. I act on it with the matrix w. Then I have non-linearity. Let's call it sigma, and then in the output I have another matrix, right? So very very straightforward. Now, what I can do, I can try to permute the order of these hidden neurons, right? So I just change the weights. So I apply a permutation matrix to the matrix W, right? Because sigma acts element-wise, I can take this matrix outside, right? And this is what I get. Right? So this is how this permutation looks like. Now you can see that if I do this permutation on its own, the functionality of this neural network changes, right? So the output will be different for different inputs. So what I need to do is I also need to permute the second matrix, right? So the weights here in the second layer accordingly, right? And these two matrices, right, being permutation matrices, they're orthogonal, so they cancel out. And you can see that I get functionally the same neural network, right? So whether it is permuted like this or it is permuted like this, right? So it's exactly the same up to just the naming or the numbering of the weights. So more generally it will look like this. So if I have an L-layer neural network, basically the weights, we can act on them on this product group of permutations along all the dimensions, right? So it acts both on the weight matrices and also on the bias vectors, right? And this will guarantee that for any element of this group, the functionality of this neural network will be the same, right? So there are actually a lot of these symmetries. They're hidden. People knew about this for ages, right? So this is one of the reasons why we have this kind of energy landscapes with a lot of minima. But I would say that it has only been very recently that people tried to learn, to look at these weight spaces systematically and actually try to take advantage of these structures, or at least to the best of my knowledge, right? So let me show you in the remaining few minutes how we can take advantage of these structures systematically, right? So let's take a look at how we train neural networks, right? So typically we minimize some loss function, right? So we have our training points, right? So this is the input, this is the output, belonging to some batch, right? I have my loss function, right? I minimize it with respect to the parameters theta, right? The weights of the neural network. So I sum the loss, right, or average the loss over the batch, right? And this is what I'm trying to minimize when I train the neural network, right? So I do it by typically by backpropagation. So I need to compute the gradients of this loss, and the gradients is basically sum of the gradients of each the losses of the individual data points, right? So this is how it looks like, right? So I denote by U, and U the pre-activation input, and by A the output after the activation, right? After the nonlinear function. So basically, this is the expression of the gradients. Now, if I look at this structure, right? So this is the gradient of with respect to the weights of the else layer. So I can write it as this tensor. So it has the dimensions of DL, right? So the size of number of neurons in the L layer, number of neurons in the L-1 layer, and that's the size of the batch, right? Now, you can see though that there is redundancy in this structure because the gradient itself actually for each data point is rank 1 matrix, right? I can write it as the product of these two vectors. So we carry along these kind of matrices, and they consume a lot of space, right? And also, what is not nice is that if we were to permute the neurons in every layer differently, right? So as given by these permutation groups, actually I have two permutations acting on this matrix, right? So of the current layer and of the previous layer because of the structure of the matrix, right? And also, of course, permutation of the samples in the batch, right? I can put them in any way I want, right? Because it doesn't matter; they are all summed or averaged. So the more convenient representation is to represent the gradients as these vectors A and G, right? And basically the gradient is given, this matrix is given as their outer product. So here the dimensionality is always 2, and we have the permutation matrix only of the dimension DL that acts on that acts here, and of course the permutation of the data points in the batch, right? So this is the group that acts overall on this space of gradients. Now, what do I do with neural networks that take gradients? I can do many things. I can do model optimization, right? So I give you the first gradients of the neural network, and then I can predict the new one, right? So this is how optimization algorithms work, right? So if I want to accelerate my optimization algorithm, I can produce directly the update of the weights, right? So if I want to do things like fine-tuning or model editing, I can also produce some scalars, right? So I can, for example, compute second-order quantities like curvature, so I can do model analysis. So this is an example of optimization, right? So this is how the stochastic gradient descent will look like. So again, this is some low-dimensional representation of some high-dimensional function. And this is what we can learn with this approach, right? So a neural network that consumes the gradients as input. And here are some examples on more realistic data sets. And you can see that it works significantly faster. So the neural network trains significantly faster than with standard approaches. Now, another example, so when you have a very big model, right, like an LLM, so transformer with often tens of billions of parameters, right? So we have a huge matrix of the weights in this transformer, right? Let's say it's of size n by m, right? That might take a week on a cluster of GPUs to find these parameters, right? So nobody, unless you're Google or Meta or OpenAI, really have the computational capability to find these matrices, right? So people use models that are pre-trained, and now you want to fine-tune your model to some specific task. So how do you do it? You do it by what is called low-rank adapters. So I cannot afford to compute again or fine-tune these weights, so I will update them by a low-rank matrix that I can write like this: U V transpose, where U and V are of rank 1, of rank R, right? Which is very small compared to n, right? So here the number of parameters will be linear rather than quadratic, right? So I save a lot of parameters in this way, right? And the way that fine-tuning is done, I freeze this matrix, so I assume that it's given, and I update, I train just these lower one components, right? So this is called parameter efficient fine-tuning. There are many approaches and many ways of doing it, and this is what is used in practice in the industry. Now, if you look at this matrix, you can see that there is interesting symmetry here as well, right? So any invertible matrix I can put here will not change the functionality, right? So I can multiply U by R and V by R inverse, right? So basically it's defined up to general linear, right? Or any subgroup of it, right? So any rotation, for example, or any permutation, right? Will also be an invertible matrix. So we can do what we can do with this approach. We can do models that learn on low rank adapters, right? So this is called low learning on LoRa's. So you can have start with a pre-trained model, and you can try to find, basically take as input the low rank adapters and train a neural network that predicts some useful properties from these LoRa's, right? For example, I can predict accuracy after fine-tuning by these LoRa's, right? So you can see that if I have a good way of doing it, I don't need to do training by backpropagation. I can just tune the parameters. I have a small model that tells me the accuracy on the test set that I'm interested in, but for different choice of these adapters. So I can choose the adapters based on this function rather than the original network that will be extremely heavy to backpropagate from. And actually, the claim is that we have a lot of data to learn. So this is a visualization of the Hugging Face universe where we have millions of different neural network architectures. There are weights that are saved and shared. So basically, this is an interesting new data modality. Neural networks that take other neural networks as inputs, right? Or more correctly, they are weights. And the weights have interesting structure, so we can design interesting geometric architectures that have equivariance with respect to all the transformations that exist in these parameter spaces, and we can do many interesting things, more efficient and more accurate, for example, fine-tuning or prediction of properties in these neural networks. So I will show one, so these works were done with by my student, Yoav Gilbert, in collaboration with Guy Maron and other collaborators. So this is also one of the last things that I would like to mention. So these are drag and drop LLMs, also collaboration with many people from China, where basically we try to avoid fine-tuning by basically learning to generate parameters directly, the low-rank adapters, low-rank matrices directly, and you can see that we get here similar accuracy to the full fine-tuning, but orders of magnitude cheaper computation. So I think I'm out of time, so I can conclude, right? So maybe they have not lived happily ever after, but at least the story continues in interesting ways, and now it is happening in the weight spaces. So if you're looking for interesting ideas or interesting applications where all these geometric group theoretical approaches, equivariance and so on, might evolve, I suggest you to look at the spaces of the parameters of the neural networks. And in fact, a few months ago at iClear, we had the first workshop on weight space learning, so it is new, but I think very rapidly growing and very rapidly evolving little community. So I will stop here, and thank you very much for your attention.
Hi. Firstly, thank you for the beautiful talk. It was very, very nice. What I wanted to ask about was, what were some of the most exotic types of Lie groups that you encountered in the research? So, I guess, for example, you did encounter rotation groups, which is like orthogonal groups, and there's also permutation groups. But what about, say, unitary groups, which happen in complex cases, and what about, like, say, symplectic groups? If we like open our mind and like maybe it goes exotic like that.
Yeah, good question. So I think unitary groups probably Jeff would know better. So people working in physics, I think that's where you encounter them. So in crystals, wallpaper groups. So basically infinite symmetries, right? So that's where what people work with. So more exotic things, products of, for example, SE3. So when you model the backbone of a protein, you can think of it as rotations of the heavy carbon atoms with respect to each other. So you can think of it as SE3 to the power n.
SC3 is the rigid motion group, right?
Special Euclidean group. Right?
Yes.
So
yes.
no reflections, because reflections
Yes.
they're physically impossible, or they change chirality of the molecule. So basically we have flow matching genetic models that generate protein backbones in these spaces, so by using Riemannian flow matching.
What about, say, possibly do you quotient it up by some subgroup and then it becomes a weirder group?
Yeah, so people do it as well. So people do it, basically, you can do all sorts of, for example, stabilizer groups. So there is an entire theory of steerability, general steerability. So the works of, initial works of Taco Cohen, and then Pim de Haan from Max Welling's group. Yeah, you can also take it more generally to category theory, so to generalize geometric symmetries with more general notion of invariance. Yeah, so there is a lot of exotic things that some of them I don't fully understand.
Thank you.
Hi. Yeah, thank you very much. I just want to kind of counter a little bit your point on symmetry, because you emphasize basically, is symmetry useful to approximate something, or is it faster? And I think if you come from physics, you will see that it's not the issue whether something is fast, it's the question is whether you learn something from it. So I think theoretical physics, the role of symmetry is not to kind of do something fast or quick or whatever, it's actually to provide profound understanding. So if you come to the interpretability of your results, groups or other algebraic structures or whatever, it should be really, really important, rather than just try to fit something that quickly fits something. So I think there's actually much more to it.
Yeah, I agree, and I think speed is not the main consideration. I think sample complexity is the main consideration. So when you have text, right, so you can argue that you have an unlimited amount of training data, right? So you can scrape everything from the web. When it comes, for example, to chemical data, it is actually very expensive to obtain new data points. So you do want to be sample efficient. In some cases, you can solve it by data augmentation or by synthetic data, but in general, this is not necessarily easy to do. And then, of course, as you were saying, so to guarantee some properties, right? So physical properties, that your system is physically correct if it respects certain symmetries or corresponding conservation laws, might be very important.
I think for physics, the understanding somehow is related to the symmetry somehow. So when people say theoretical physics is symmetry, it's not just a tweak, it's kind of structural. So the question is like how to kind of extend this in other aspects. But I think it's not a done deal, because
no, it's definitely not a done deal. And in many cases, so first of all, in many cases you don't know the actual symmetry. It might not even be a group, right? So a group can be just a convenient model, and there is a trade-off between how much you build into the architecture and how much you want to learn, right? So convolutional neural networks, again, are a good example, because translational symmetry is a very naive way of thinking of the transformation that images undergo. And yet it's convenient to build it into the architecture, because you get very efficient architectures on the hardware that exists or existed historically. Of course, everything else is learned by, for example, using data augmentation. Right? So AlexNet, for example, that achieved a breakthrough on the ImageNet benchmark in 2012, used very sophisticated data augmentation accounting for transformations that you cannot model as shifts.
Thank you for a really inspiring talk, and it's beautiful how everything fits together except the positional encoding from transformers. Is there any way to squeeze this in, to amend it, to make it somehow better? And
so you can do positional encoding that is permutation equivariant as well. Yeah. So in graphs, for example, this is structural encoding. We actually have multiple works that explore actually sophisticated way of doing, basically counting graph homomorphisms, and basically this gives you also fine-grained expressive power for graph neural networks. Yeah, so positional encoding is definitely far from being a done deal.
One last question from Ulrika, and then we can move on.
Well, first of all, I agree that somehow the symmetry should give us more understanding. That seems to be a very important point. So I just want to say that. But also, just wondering, a lot of symmetries are not really symmetries in real life, right? I mean, our face is not symmetric, and that's probably not important for recognition, but maybe it is. How do we deal with sort of, I don't know, fuzzy or quasi symmetry? Is that something that is already considered and built in, or what are the solutions for that?
Yeah, so this is a property this is a very important question. So this is a property that we call geometric stability, and the idea is that if your transformation is not exactly an element of a curve, you can quantify it as some distance from the curve, right? So if you're epsilon translation, for example, right, in some sense, you want the function to be continuous with respect to this perturbation, right? So if I'm almost translation, I don't want the function to be to break the invariance or equivariance property. So this was proven by Mallat and Bruna for convolutional neural networks. Similar properties exist for graphs and for other geometric architectures. Yeah, so you guarantee that you will not get disasters if you deviate from the exact symmetry assumption.
Okay, let's thank Michael again.